Welcome, everybody. Shimok Chaudhary and IUCAA colloquium series. Today we have Professor Ranjeev Misra giving a talk on the X-ray variability of black hole systems. This is a wonderful occasion to welcome Ranjeev to our quite successful, I would say, IUCAA colloquium series. We've kept our normal time of 4 p.m. on Thursdays, and we've had people from various time zones contributing to this series, people who are in reasonable time zones for this time. And we've had some really interesting talks. I was, in order to introduce Ranjeev to many of you who are online, I can see the names of people. Ranjeev knows my introduction. I just asked Ranjeev, since when has he been in IUCAA? And he said, since the Big Bang. He essentially has been in IUCAA in various roles from the very beginning. When I joined IUCAA in the mid 90s, Ranjeev was a postdoc here. He'd just come from the University of Arizona, having worked with Fulvio Melia. He did his PhD there at the University of Arizona in Tucson. Then he came and joined IUCAA as a postdoc, went back to the US, Northwestern University, to do another postdoc, and joined IUCAA as faculty in 2000. So he's been here 20 years. That's long enough since the Big Bang. And then Ranjeev plays some really important roles in IUCAA. I see a lot of people who are in the audience today who are our associates. And Ranjeev has had worked with people in universities from the very beginning and plays a very important role in that. He's in charge of all the conferences and workshops that are held in IUCAA, and together with the Dean of Visitor Academic Programs, Kandaswamy Subramaniam, Ranjeev handles a lot of our relation with the universities. He's in charge of has been in charge of the old IUCAA centers in various places, and now the new iCards are his idea, and through them we reach out to the rest of the country. So, but Ranjeev also, in his scientific capacity, has been one of the major people driving the agenda for AstroSat research. And today he will talk about what advantage the AstroSat gives us. Over to you, Ranjeev.
Thank you, Shamak. Uh, Welcome, everybody. This has been a monumental week for me. I think I'll remember it for a long time. It was this week that I gave my first two talks on Zoom in lecture courses, that is, teaching lecture courses for a summer school. And here I am giving my first scientific talk on Zoom again. So these are all new experiences for me. So please bear with me if I make any mistakes, both technically and otherwise. Otherwise, let us go ahead. And the main thing I'm going to talk about today is AstroSat. I'm not going to talk about what is AstroSat to this audience. Everybody knows that. And because I'm going to talk about AstroSat, I must put in a word of acknowledgement here that, as we all know, AstroSat was launched by ISRO. Its main payloads were built by several different institutes of the country. There were hundreds and hundreds of engineers who have worked for this. There are the payload operating centers which are working continuously 24/7, making sure we get data from here. And on top of it, there is this huge group of people who are analyzing data, making sure that data works out and all. So all the results which we get from AstroSat cannot be attributed to any single person or group. It is really a joint activity, and it's a proud moment for us that we are getting so many good results from there. And one of the important groups of this is also all the uh, students and postdocs who have been working on trying to understand and analyze AstroSat data. And even if any paper which comes out of AstroSat helps the other field papers as well, because it gets the system to be much better calibrated and better recognized as a system alone. Having said that, I will, since this talk is about AstroSat, I can assure you that, or let me tell you that all the data which I show in this talk, each and every single one of them, will be from AstroSat. So I will not specifically mention anytime I'm showing any data that whether it's from AstroSat or not. it should be understood that this is from AstroSat. On the other hand, there are a lot of things I'm not going to talk about, so let me mention them first. AstroSat has many instruments, especially including the Ultraviolet Imaging Telescope (UVIT). It's been producing fantastic results, telling us about faraway galaxies and nearby stars and star-forming regions. And I'm not going to talk about anything about that. I'm going to focus more on the X-ray instruments here, and even the X-ray and hard X-ray instruments here. I'm not going to talk about the CGTI, which has given some groundbreaking work on polarization and X-ray polarization for the very first times at that level, and about the direction of gamma ray burst, which I'm not going to talk about here. Even among the rest of satellite, the soft X-ray telescope and the large LAXPC, which is going to be the main focus of what I'm going to talk about, I'm not going to talk about the great work these instruments are doing on studying active reactive nuclei, and they are doing that in conjunction with the UVIT, and some fantastic results have already come out of this place, and that could be a very well separate talk by itself and extended period. Instead, I'm going to focus on AstroSat results on X-ray binaries. But again, to repeat myself, even in X-ray binaries, I'm not going to talk about the science which is being done on neutron stars, which is an astrosat niche by itself, and especially the measurement of the cyclotron lines and measuring the cyclotron lines in different pulse positions, which is one of the hallmarks of astrosat. Even neutron stars, where we have seeing the rapid variability of sources, is something which is quite groundbreaking, which has been done in astrosat. I will not be talking about that. All this is for interest of time and for interest of clarity. I'm restricting myself to just talking about astrosat results of black holes. At least that is what I thought I will do. And then I found that even that would be a little too much. So I have to select and only presenting a very few of the astrosat results of black hole systems. So that gives you a perspective of what fraction of this wealth of data I'm talking about. So actually, essentially, this here is a painting of a black hole binary. The black hole sits right in the center, a tiny little spot here. You have a regular star, matter from regular star falls towards a black hole. It has angular momentum, so it goes around the black hole, and because of turbulent viscosity, it forms an accretion disk. And of course, it's not the black hole, but it's the accretion disk that we see. So the center theme of all the studies is this accretion disk, which is this red, white, yellow thing going on, which is cold in the outer front and becomes very hot in the inner regions, and the X-ray emission comes from there. So the accretion disk is the essential theme for this thing. Well, this is not new. In fact, we have something called a standard accretion disk model, and there are two publications here, which I will spend some time uh, talking about them, not talking about what they actually did, but talking about them. The first is a fantastic paper which came out in 1973, published in ANA, I think reprinted from a Russian Soviet Union version by Shakura and Sunev. And this is considered to be the standard accretion disk theory. And uh, what it did was, although we did not know turbulent viscosity, we parameterize it in terms of parameter called alpha, and that allows us to calculate what a spectrum and things would be like from a disk. This was amazing breakthrough, and this allowed a huge science to come out. However, let me point out certain things interesting here, which I've mentioned here. In terms of ANA papers also, this is a longish paper, 18 pages. And if one reads through those papers, you realize that there are 8 sections in this paper, or 6 or 7 or 8 sections in the paper, whether you include the appendix or not. And each of those sections have given, and only one part of the section is what most people quote as a standard accretion disk. There were many other parts of this work which have given out by themselves whole fields of astrophysics in the range. And so it was quite an extensive work done in 1973 by Shakur and Sunev on this work. And it's a, I mean, I just showing for a younger audience that you should see how much when they started a subject, it nearly completed. In fact, there's sections here which I, in this paper, which will become uh, topics and astronomical topics by themselves, not now, but maybe in the future. Amazingly, and 1 year after that, but not really, uh, there was another paper which came out, which is Novikov and Thorn, which was an extension of the standard accretion disk model. What they did was, in within 1 year time, and which may not be true because I feel that most of the work was done in 1972, and so they had prior information about chakra Sunay results. They did a complete work in full general relativity. That is, they solved a whole accretion disk solution for a curved black hole space-time, and they did it within 6-7 months. The other thing I would like you to note is that this paper was 107 pages long. First of all, this was a lecture series in the Lehus uh, conference in 1972, where there were other great papers from Hawking, Bardeen, and Cooper on general relativity, and this was by far the biggest work that was done in that great conference which was held at that time, great lecture series which was held at that time. This is 107 pages, and it's a wealth of information on what one can do with accretion processes over black holes. And to do this in full GR was really quite a accomplished task. However, I don't usually think citations always have a uh, impact on understanding of the importance of paper. In both these cases, is not. But I just brought out one factor that the Shakrasana paper has been cited 9,687 times last I checked. And there is rumors, I don't know whether it's true or not, that this is the most cited astronomical paper ever. And while the Novikov Thorn paper is 626, substantially less over a time period. In fact, in my opinion, the lot of work which Novikov and Thorn done was locally or at that time was found to be totally irrelevant. Nothing of very few people realize or consider that work to be important at all in that work. Everything was based on Shakov and all those citations of 626 which came early were just for kind of they cited Shakov and Novikov and Thorn together. My talk is going to tell you that how important it is that they work for 107 pages and they did not get that much. It was, people were challenged at why it was that important at that time, and how now, after nearly 47 years, the Novikov and Thorn paper has become now more important and substantial than the Shakur and Sunay paper. And so things take a long time to germinate, and when they germinate, important things become absolutely great and all that. So during the end of this talk, I will show you how the main results which we are getting now from AstroSat, which are now violating the Novikov and Thorn results. So we'll wait for that. But before that, I'll have to give you an explanation of why Novikov and Thorn paper was not important, why general relativity correction was not considered important, and why Shakura Sunay solution was considered to be a great thing. This goes from this painting which we have here, and this is, I must remind you, is a painting, and this is completely false. This is a picture of a black hole binary. What we really know, even now at this time, is something more like this. This is what we really understand of a black hole binary. What we have in the left hand side is what I've marked here as a cold disk, and this is the standard Shakura Sunay accretion disk. And what we believe is that it truncates, it stops at a certain radius. This is a black hole here, and the black dot here. The cold disk stops at a certain radius, and then there is this inner region here, which is often referred to as a hot disk, corona, and etc. And nobody really knows what this is really all about. And this is the kind of geometry and this is the kind of our knowledge at present place and not the detailed painting which you had shown earlier. How do we know this, that this is the case? that when you look at a black hole in a certain particular state, which is called hard state, what you find is that you get very high energy photons, X-rays, about for X-rays in about 100 keV coming from there. And this, one of the few non-controversial topics in the field, is that this is due to thermal combination. So what is happening here is photons from this standard accretion disk, which we now call cold, because they are temperatures of 1 kiloelectron volt. I'll remind you, 1 kiloelectron volt is about 10 million degrees, or while the hot disk is about a billion degrees. So from the cold disk, cold photons or the low energy photons get upscattered, and we see a spectrum like this. And from this kind of a spectral condition, we believe that this is the geometry from the system. This has been known for the last 40 years, again 50 years, that this has been proposed, but so far this is our present day knowledge on here. But the topic of my colloquium today is variability. And here I'm showing you data from a very famous black hole source called Cygnus X1. And as you can see that it is varying. And mind you, there are no, the error bars on these curves are there, but they're so small that you can't see them. All these lines and these wriggles you see are real variability of this source. So these sources are extremely highly variable. And when you look at a light, this is called a light curve, that is counts per second, how does intensity go with time, you can't really make out anything from this. But what we can standardly do is we do a Fourier transform. When you do a Fourier transform of this and then take its amplitude square, you get something called a power spectrum. And the power spectrum tells you characteristics of this temporal behavior. So here are two power spectrums of Cygnus X1 taken at different time, January 2016 and June 2016. And what it tells you is that this source is showing broadband kind of noise. There's nothing peaking out here. And the shape of the power spectrum changes over time. But it has bumps. These bumps seem to signify certain important frequencies, and one of the great mysteries is still to identify how these frequencies are, and we'll come to that more later. Such a power spectrum, although this is of course AstroSat data, has been known beforehand, earlier. But what was the real advantage of this was, now we can study the behavior of this kind of sources like Cygnus X1 in very different energy bands. So right from 3 kiloelectron volts to about 80 kiloelectron volts, we can now study how does the power spectrum varies. In fact, that may not be the right appropriate way to do this. What we do is we find the variability as a function of energy. So on the left hand corner, you can see that we can plot the fractional RMS, that is, what is the root mean square variability at a given energy, which is in the x-axis. As a function of that energy, you can see how the fractional RMS in this case is decreasing. And this we can do at different frequencies. So for example, this curve is for at 0.1 hertz. Not only that, we can measure the time lag. That is, if there is any time delay between the high energy photons coming and the low energy photons coming between here. The right hand side shows that the time lag plot between, let's say, these high energy photons at 40 keV compared to 5 keV photons in the whole spectrum. And this you can do it not only at one frequency, you can do it at different frequencies. And for example, here we are plotting the same diagram, the fractional RMS and time lag, for 3 different frequencies in this plot. This provides a very rich source of information which was not available before, by which we can now model, and now we can find out what is the behavior or what is the cause of this kind of a behavior system. So to that, let me go back to our basic model, that you have a cold disk and a hot disk, and photons from the cold disk enter the hot region and get combined to produce this. Now, to have variability, something must be changing. So let us first assume that the temperature of this cold disk, inner disk, is changing, or the number of photons going in other ways, or more precisely, the number of photons going into the cold disk is changing. If that happens, then as the number of photons increases here, the hot disk one will cool down. So if I increase the input of the cold disk, the high energy photons will go down like this. And if I increase it further, it will go down and become flatter. So I can show it to you in one flat curve like this. That suppose you started off with a spectrum like this and you kept increasing the coldest photons, this will increase and the high energy photons will come down. Which would mean that if I plot the RMS or the variability as a function of energy, that would be a curve which is going down like this. So if I see a curve going down like this shows an indication that the cold disk temperatures are cold disk photons are actually varying. Sorry. On the other hand, it's also possible that the heating rate of the hot region or corona increases or changes. If that happens, the there will not be much change in the low energy photons, but a lot of change in the high energy photons. So they will just keep going up like that. So here's a figure. If you start off with a spectrum like this, increase the temperature, the high energy photons will keep going up, while the low energy photons will remain the same. In this case, it will be inverse, that the variability will be higher in the high energies and lower in the low energies. So the RMS as a function of energy will increase with, and these can be, as I'm showing you in the figures, can be correctly predicted. Because we know the spectrum, we can actually correctly predict how this curve should look like. In reality, of course, this is how it will happen, that you have, it should go, if there's change in the seed photons, the RMS will go down. If there's change in the heating rate of the hot disk, the RMS will go up. In reality, you can have both of them. You could have the cold disk varying as well as the hot disk varying out there. In that case, you get a sum of the two, which could be either going up or down or flat like this. More importantly, if there's a time delay, suppose the disk varies and after some time delay the hot disk varies, which we expect, because if you have a perturbation which is coming from outside inwards, it will perturb this cold disk first and then later perturb this hot disk. So there'll be a time delay in between these two, which would mean that we would see a delay in the photon arrival time depending on energy. And this is what you can see here, that this is phase lag, but this is also time lag as a function of energy, that these photons will be delayed compared to the low energy photons depending on what is the time delay between the cold disk and the hot disk. Now, armed with this kind of thing and with AstroSat, armed with this kind of formalisms, which we have to develop, it is you have to do it numerically to find what should be the really effect of this. We can now actually go ahead and fit the spectrums, fit the RMS versus energy, the time lag versus energy, and at which we do at different frequencies, so we can get to know what the variations in the hot disk temperatures are, what are the variation in cold disk temperature, and what is the time lag between them. So this is a step forward, and I'll explain a little bit more why how this is a step forward in our understanding of the systems are. Before that, just showing you as an example that was for Signal 6.1. Here's another example of another black hole source, Maxi J. It has a completely different kind. The black line is for the other black hole source, Maxi, while the green and red are for two Signal 6.1 at two different times. The power spectrum has completely different shapes, so the nature and variability of these sources are constantly changing within itself. That means a single source can change in time, and different sources show different kind of variability in the nature. And what you can do is, for different sources, you can still find how does, now with this formalism, how does the hot disk temperature vary, what is the RMS variability of those hot disk temperature as a function of frequency. So, and you can see that these kind of shapes and all tell you what are the nature of this of the variability which is coming in and propagating in a more direct way than you will see it from the so we can also find what is this is the ratio of the cold disk temperature and the hot disk temperature variability, how they're varying, and sometimes we see remarkable similarities and sometimes we see complete different behavior out there. We can also see what is the time difference between the cold disk variability and the hot disk variability, and it is very interesting to note that the time difference between the variation in the outer cold disk to the hot disk depends on the frequency of the variability or the variation or the oscillation frequency of at what you're wearing it. This seems surprising, but not really, because in cylindrical systems, frequency dependence of travel time is well expected, and even for a sound wave which is traveling in a cylindrical wave, the sound speed is not constant, and it things travel at a different rate depending on the frequency of the sound wave itself. These are not sound waves, but that was just an analogy in our system. So overall, we have made some kind of progress. That what we had initially was just a bundle of power spectrum and photons and light curves. Now we have converted them into physical parameters like temperature variations of the disk, temperature variation of the disk, time lag between the things, and we can study them as a dependent frequency. And this goes back as a major feedback into more sophisticated numerical modeling in the times. But the more interesting part, another interesting part, not more, another interesting part of black hole variability is the fact that they show oscillations. And the power spectrum of many sources have very strange things which are called quasi-periodic oscillation. Here is a very good and famous example. That if you take the power spectrum of this black hole, very famous black hole source called GR715 at a particular time, instead of seeing a broad feature like this, you will see a very sharp peak out here. And if, of course, if it is a delta function, then this would be a periodic oscillation. But it's not a delta function. There is a width to it, and this width is real. Therefore, this kind of variation is called quasi-periodic oscillations. Often, these quasi-periodic oscillations sometimes also have an harmonic, as you can see here, which is observed. These, I will talk a lot about these QPOs in my coming part of the talk, and these but the very first nature would tell you that this must be something to do with the characteristics of the disk and give us a wealth of should give us a wealth of information about what is happening. We had known this prior to AstroSat, but and we also knew that this frequency is not a constant for the same source. If you look at it after half an hour, 1 hour, this frequency varies and it can change. It can go from, as you can see, these are three different observations of JS915 separated by a few hours only, I think. And you can see that the frequency of this quasi-periodic oscillation keeps changing with time. So it's a very dynamic, variable thing, if you can excuse the word. More importantly, you can what we can do with AstroSat is this power spectrum can also be generated in various different energy bands, which was not possible before. And this, provided we can see these QPOs in different energy bands, is giving us a wealth of information about what is the radiative process which is active in these systems and how do we interpret these radiative sources correctly in the field. For example, you can do exactly what I said before, and you can start modeling the time lag. Suppose for, and this is another black hole system, Swift J161528, which also shows a very nice QPO and a subharmonic, amazingly. That is why it's called a subharmonic, is that this is half this frequency, but its amplitude is lower than that of the second one of this peak. And you can find the RMS as a function of energy for these QPOs. You can also find a time lag between different energy bands for this QPO as well as for the subharmonic features. This, using the same models which I talked about kernel heating and temperatures, you can interpret them as variations in both the temperatures uh, of the hot disk and the kernel disk, and then there is a time lag between them, which is causing this kind of variability in this whole pattern out here. So overall, we are making progress here in trying to understand this behavior. As you can, as I'll, you can see here that although we have made such a understanding on making a step forward, that we have now got to know what exactly is varying, like which is the temperature, how is the temperature of the corona and or the hot disk varying with compared to that of the cold disk. we still don't have a complete picture of this system, and that is because of the confusing ideas about the various different ways by which these systems vary. There seems to be no uniformity, and things can vary in a very difficult manner. More complexities occur if you take into fact that in many systems like GS915, the spectrum also has a contribution from the standard Shakura-Sonev disk. Now, all that modeling which you had shown was done only for, if you assume that all the things we are seeing is from the hot disk, that is the compromised part. Suppose I include the cool disk part to it, it becomes much more complex in behavior. There are many parameters which come in. For example, I have been only talking about the temperature of the cold disk and the temperature of the hot disk varying. It could also be that the inner disk radius is varying during this very fast in this radius. It could also be that the optical depth is varying, and we have been trying a lot to trying and using these kind of models to see if we can predict the fractional RMS as a function of energy for both the uh, at a fundamental and high frequency at different epochs to give us an understanding of what exactly is the system is varying in there. This is very quite difficult to do for a couple of reasons. One is that we are a wealth of information. That is, there are many QPOs at different frequencies, and they do seem to behave differently, which is causing problems. The second is simple models sometimes do not just fit, and not only we have to vary just the temperatures of the coldest hottest, sometimes we have to vary the optical depth of systems. In fact, in our past prejudices, we will, I mean, from theoretical prejudices, we know that the optical depths and other parameters like the optical depth means the densities of the disk or the hot disk can vary, and these variations can cause the imprints in these predictions. So this makes it a more challenging idea to predict. But there are a lot of constraints here, such that because we are looking at QPOs and the harmonics, there are a lot of constraints you can put that they have to behave in a particular manner, and this is giving us a wealth of information there. But this is still in very early stages, and we have a fairly long way to go before we can have access to all information. And one of the ways we'll get it is when we get a more comprehensive understanding of all the observations we have done so far. This QPO frequencies vary with time, so you can you can also correlate it over spectral parameters. Like here's a wonderful example of for this. Again, this was Maxi J1535. What is plotted here is the QPO frequency in the x-axis and the power law gamma, which is the photon index in the spectrum. You see, the thermal combination looks like more or less like a power law, and if you look at the spectrum of the thermal power and the QPO frequency, you can see that there's a very tight correlation. So what it's saying is that the frequency of this of the oscillation has something to do with the how the spectrum is being generated, which should be the case, and it is highly correlated. That means the geometry of the system is playing an important part in all this understanding. You must say that I must confess that up till now I may be talking in that there's a lot of ifs and buts which we have been putting through, and that is the very nature of this subject. That a lot of these things we have still not understood completely. However, I'll go to the next part of the important thing is that give you an idea of what people have been thinking about the origin of this quasi-periodic oscillations. Uh, the first impulse when you see a frequency like this is to try and identify it with a characteristic frequency of the system. The second thing, of course, we'll do, which I'll talk about a little later, is even if there is a characteristic frequency of the system, why are we seeing a oscillation in that frequency? That's a separate question. Right now, the question is we are seeing a frequency, it must identify with some characteristic frequency of the system, and what is the characteristic frequency of the system? Or in other words, can we predict theoretically what is the frequency at which we are seeing this QPO? To do this, we can simply look at what are the characteristic frequency of the systems, and there are three relativistic test particle frequencies which are been used very extensively in this field. What does test particle frequency means? That you forget that there's accretion disk, you forget that there's anything else. You have a test particle going around a black hole in an orbit, in a circular orbit. What are the frequencies of this particular circular orbit out there? First, is obvious, is the Keplerian frequency, is the frequency at which this particle will go around the black hole, right? The second is the epicyclic frequency. Now, if a particle is going around a black hole and you perturb it in the radial direction, then this perturbation will, the particle will oscillate along the radial direction in a particular frequency called the epicyclic frequency. It is extremely interesting, of course, is known for that in general relativity, unlike Newton's law, which is an R square force, in general relativity, the epicyclic frequency is not equal to the Keplerian frequency. So, what you that's why you get the pedestrian motion of Mercury, and that's one of the uh, leading reasons why why Mercury persists in uh, leads in its persistent frequency. So the third thing you can do is is something called length chain frequency. Is that if you perturb this orbit along the vertical direction, z direction, away from the orbit, then the oscillations will also it will oscillate in the vertical direction, and this oscillation occurs is has a name of length chain frequency. This oscillation will occur and it has a particular frequency more because of, I mean, it's because of, it's only occurs when the black hole is spinning and it has a particular direction of, and a particular direction of the angular momentum of the black hole. So these are the three frequencies which are the characteristic frequencies of a system, and one would really hope, and has been a hope for a very long time, that the quasi-periodic oscillation we see is one of these frequencies. Why would that be? Because all these three frequencies are modified by general relativity, and if we identify them with the generalistic behavior, we are going to probe GR directly out here in that one. The second is, once we have identified it to be one of these frequencies, then we can at least have some idea of a theoretical modeling of how these quasi-periodic oscillations or the systems are oscillating at the first place in the whole thing. Just to that some of the models also, I mean, naturally have worked that the quasi-periodic oscillation we see may not be one of these three, but they could be additions or subtractions. I mean, subtraction of these two. One of the famous, more popular one is called the periastron frequency, which is a subtraction of the Keplerian frequency minus the epicyclic frequency. So these periastron frequency could be the, remember, the periastron frequency will be zero for Newtonian gravity. So if we identify it as a periastron frequency, the QPOs, then we are measuring directly GR effects. In any case, the length sharing frequency is only true in GR for a curve geometry, and it doesn't have a Newtonian equivalent. So this is, people have been trying this all, people have been trying to, but there have been no consensus and no success so far, has been so far, on which of these frequencies are there. However, there are some other characteristic frequency of the system apart from this relativity test particle frequency, and these comes from the understanding that these are accretion disk systems as well. So one can talk about other characteristic time scales of accretion disks. Thus, characteristic frequencies will be 1 over these time scales, and there are two important ones which are to be considered. One is called the sound crossing time, that is from a given radius r, when you divide by the sound speed, so how long does sound take to go from given radius r towards the black hole? That's the sound crossing time of the. This is a characteristic time scale of the accretion disk. The other is how long does actual matter take to go from a particular radius r to the black hole, and this is r by vr, where vr is the speed or radial speed of the material flowing onto the black hole. And these are these two are characteristic timescales of the accretion disk, and it's also possible that they would be uh, uh, possibly the cause of the quasi-periodic oscillations in the system. So we got five kind of frequencies here, which we have to compare with the, the biggest problem in all this is that the first three frequencies, depends on the radius of the at which we are looking at. And since we know that many quasi-periodic oscillations are varying in time, and the frequency changes, which means that there is no particular radius at which the quasi-periodic oscillation occurs, or the characteristic radius associated with this quasi-periodic oscillation is also changing with time. So we need to first find a radius and then see if we can compare it with the frequencies out here, and that has been proved to be very difficult. The second is that the characteristic accretion disk also obviously depends on the radius of the source, but also depends upon the accretion rate of the at a particular time, because the sound speed will depend on the temperature of the system, and the temperature changes depending on whether you have a high accretion rate or low accretion rate. This is also true of the rate of the viscous time scale, but viscous time scale also depends on the unknown viscous parameter uh, alpha. The sound crossing time RCS for certain conditions of the spectroscopy does not depend on the unknown alpha viscosity parameter. So this was the status up to now, and it has been very very difficult to figure out. And people have been arguing for which of these kind of frequencies correspond to which QPOs. And in fact, there is such a large number of QPOs that one can associate nearly all of them with each other. The difficulty here is to measure the radius and the frequency at the same time. One can measure the inner disk radius, but for that you need to have very broadband X-ray spectrum that is covered nearly all the way from 1 to 80 kV, and this was not possible before AstroSat. AstroSat gave you the advantage of having 1 to 8, about 40 to 50 kV here, and with this kind of a spectrum, you can actually measure the radius quite accurately out here. If you did not have this low energy part, you would not be able to measure radius that well in the whole thing. The ultimate advantage of AstroSat is that while some other combination of instruments can give you such a wide energy spectrum, you should measure the quasi-periodic oscillation at the same time. Remember, the quasi-periodic oscillation changes in timescales of hours. So if you see a spectrum today and you're looking at the timing after a few hours, you can't compare them. It has to be simultaneous. So, and simultaneously, when you're looking at the spectrum, we should be able to see the frequency, and this has been the AstroSat advantage of that. When you're fitting the spectrum, we get to estimate both the inner disk radius and the accretion rate from the systems. And so from now, and at that same time, we are measuring frequency. If we do this for a large number of observations, we have frequency, accretion rate, and the inner disk radius, and we can start seeing what is the relationship with how does the frequency change with radius for the first time. So this for the famous black hole source GRSN 15, on what is plotted here is the frequency observed versus the radius inferred from spectral fitting. As you can see, there's a correlation, and there's expected correlation, which is good, that as the radius increases, the frequency decreases, which we should expect in some broad physical terms. However, there is very large scatter. Although the error bars on radius are large because the spectral fittings are cruder and there are no uncertainties, the frequencies are measured quite well, and you can clearly see that despite all this, there is a significant scatter between the QPO frequency and radius. More is QPO frequency versus accretion rate. This is what is plotted here. QPO frequency and the accretion rate here. There seems to be very, very wide scatter, and there seems to be no relationship between the two of them at all. However, because we have measured both the radius and the QPO and the accretion rate and the QPO frequency together, what you can find is that sorry, if you divide the QPO frequency by the accretion rate, then please ignore the lines right now, but you can see that these data points are now much more compact, and they're much more correlated with each other in a kind of a monotonic fashion out here. This was an important finding, and this could only be possible because of the broadband coverage of AstroSat and at a absolutely simultaneous measurement of the QPO frequency at during the time when we were making the spectral measurements. The most interesting thing is that this is not surprising, but this was actually predicted, and it was predicted in that 150-year-old 150 pages paper published 48 years ago by Novikov and Thorne. Novikov and Thorne derived dynamic frequency, which is the inverse of the sound crossing time, that is R by CS that I talked about. That is the sound crossing, 1 over the sound crossing time at a given radius is indeed given by this F dynamic. F dynamic divided by the accretion rate, m dot 18 is the accretion rate, is a function only of the radius. This is the mass. We know that the mass of the black hole for this case is 12.4 solar masses. We know that very well. And these things, A, B, D, E, L, are analytical functions of the radius and radius alone. Radius and the spin of the black hole. So APDEL are the functions of the radius and spin of black hole. The expression is written in this way such that if ABDEL are 1, then you get the Newtonian limit. And the behavior of this function should be proportional m dot, but should go as r to the power minus 2.5. But these functions, which are functions of analytical complex functions of analytical functions, not of radius and the spin of the black hole, make it deviate from this minus 2.5 structures. But note, the frequency divided by accretion rate is a function of radius, and now we can test this out directly by plotting it along with what we find a correlation. The black line which we see is the predicted one when you consider a black hole with a spin parameter of 0.97. It is quite remarkable that it fits it very well with this kind of data we have, and the fact that we have found that the QPO frequency is divided by the accretion rate is the key point here, which is the 48-year-old prediction by this thing, confirms, in my opinion, totally that this is the dynamic frequency identification. It also gives you an independent measure of the spin of the black hole, where this blue curve is the one which would have been if the black hole was spinning at a equal to 0.99, and the red one was if it was spinning at 0.91, and they clearly do not match as well as the one which is 0.97. So we can kind of roughly measure it to be 0.97, but that is, I think, an aside point. The most interesting result out here is the fact that we have now identified this QPO as due to the sound crossing time from the, and we have also verified that what was predicted 48 years ago by General Relativity is more or less fitting with now with this data out here in the whole region. So I'll go into 2 levels of summary. So let me give you a broad take-home message from all this. We are seeing black hole systems vary, and we do not understand how they are varying out there. So overall, in the scientific community for the last 30, 40 years, there have been 3 approaches or battles which have been being launched, and over a large number of scientists to tackle the issue. One of the ways is to do actually theoretical simulations, hydrodynamic simulations, and of course we realize that right now it is very important to do magneto-hydrodynamic simulations because you have to understand how the turbulence happens in the first place. And this is a bottom-up approach where you use fundamental physics. I mean, you understand the system from fundamental levels and all. The second approach is to take QPOs and other broadband sparse spectrum, look at the frequencies, and identify these frequencies with characteristic ones. And this is will, like as I give an example, this would give a permanent idea about why the systems are varying and what is the system varying for. The third one is identifying the spectral component parameter, that is whether the temperature or the time, or which the temperature or the optical depth, or what is it actually varying, and how do the time lag between them is driving the variability. This third part has been a really beginning of this field has just begun with AstroSat, and it was only possible with the broadband coverage of AstroSat that we can cover this kind of approach of studying this. Even the second one we have been doing very well because this broadband spectrum of AstroSat has allowed us to measure the spectrum and to measure the characteristic expected frequencies from the system out there. And we have the magnetohydrodynamic simulations which are. However, I must confess that although we are doing all these things, a comprehensive picture unifying these three things have not been happening. Magnetohydrodynamic simulations are still in very primitive stages. There is, I mean, uh, people will not like me if I call them primitive, but the essential idea is that they are very far from actually explaining observational features in the field. We are still trying to, as I come to try to understand why a disk forms, and we have struggling trouble have understanding where does the magnetic turbulence, I mean, the turbulence itself is arises and how is it sustained, and from the very fundamental level, some great progress has been made here, which could be a separate talk by itself in the whole thing. Then, uh, uh, while we have identified observed figures, there are a large number of QPOs and all which we have not identified with, and this will take a long time to do so and a lot of hard work to be done on the new field of opening up the connecting the relative process with the timing property is just started, and we have a new instrument on space on the International Space Station called NICER, is an American instrument, and this is complementing AstroSat very well because it has a very good coverage in low energy rapid variability and simultaneous observation. This will give, but we still are a long way away from making a comprehensive story about this, and so we have to stay tuned for the next. Now, before I stop here and go for questions, I know I'm not sure whether there'll be any questions from your side and all. I have a lot of questions, and I thought I might as well put them down in case any of you would want to know that. And I can tell you that the answer to I'll just go through them very briefly right now. The questions which I have, and I think that answering them will be a major challenge for the next 5-10 years, and will be challenge and interesting to us. We still don't know why there's a truncated inner disk radius. There are many theories and all. Magnetohydrodynamics is not telling us why it is there, and hopefully it will reach a level where we can do it. Perhaps we need some more fundamental understanding of why a disk gets truncated, and this is a long outstanding problem. We do not understand why different black holes and even the same source show such a variety of temporal and spectral behavior. See, this is surprising because black holes are simple objects, and you're throwing matter into them. So only parameter you have is how much matter you throw into them. And angular momentum is anyway you know what angular momentum you thrown at them from the orbital star. So why are they showing so much different kinds of behavior has been a mystery, and we have not been able to solve it. Obviously. Why are there there's so many different kind of oscillations, characteristic frequency? What do they each correspond to? Example, Yerzin 15 shows a very high frequency QPO at 67 hertz, and it doesn't move much. It is at 67 hertz, and nobody has been able to figure out what the 67 hertz means. What is this? It doesn't. Why is it at a characteristic radius? And what is the radius it corresponds to? And what is so essential about radius? We have not understood. Here's a tongue-in-cheek question: what are these things called jets? I don't know if anybody knows about what these things are. Jets. I know a lot of people have statement like jets are relativistic particles moving around, all that. But how are they powered? What are they really made of? I think we have very little understanding. At a more fundamental level, we can ask the question: why do we have a disk at the first place? Which comes from statement like turbulent viscosity. A very famous candidate is called a magnetorotational instability, which causes this turbulent viscosity. Magnetohydrodynamic simulations are undergoing for doing this thing, but we are still not sure whether what really is the cause of this, why the disk is forming at the first place. So, at a fundamental level, it's going to be a long way before they can actually help us answer these more higher level questions which are on top. And finally, we have a little philosophical question that will we or have we already, depending on people's point of view, verified GR? And what about non-standard gravity? Are we going to go ahead and verify uh, uh, higher order gravity theory by using these techniques and checking out? These are unknown things, but there's so many questions here that we don't know the answers to. So since I do not know the answers to these questions, I will leave it at here, and I will thank you for your attention.
Thank you very much, Ranjeev.
Yes.
Great, very clear talk. Uh, and now I invite people to raise their hands in the Zoom thing and for questions. And I'll unmute you one by one. Uh, Paul, can you unmute yourself? Hello?
Yes.
The
Can you hear me?
participant.
Yes, please go ahead.
Yes. Yes, because
About the to find any
speak slowly, please. Slowly. We have
is
connection.
it possible to find any time study?
Because could you write your question in chat, please?
Yeah,
Okay.
because
Okay.
we can't make out exactly. Because,
I forget.
okay, let's try to do that. Meanwhile, we'll go to the next question. Can Nishalai Chowdhury, can you unmute yourself and ask the question? Hello?
Hello.
Yes, yes, Krishna.
Hi, Ranjeev. First of all, thank you for this colloquium. It was a wonderful presentation.
Thank you.
First question, I have three questions. I'll be quick on those. First of all, could you please go back to the second plot that you showed where you presented QPO frequency versus radius?
This one, yes.
The
This
second
one?
The second one.
Oh.
Where you join with curves. Yes, okay, this one. My query is, it's a two-part question. First of all, the HS, can you kindly clarify if it's hard state or high state?
This would be the high state. I think so.
Okay,
Yes.
high state. Okay, that answers one question. Second would be about the spin. You said that we could theoretically we could constrain spin using QPOs. Given that the error bars against radius is so high and the extrapolation to the left of the curve seems it's not fed enough with ample data, how far do you think it would be possible for us to constrain spin using QPO?
Oh, this is evident in a figure. I've also plotted the what is plotted here is in the blue is for 0.99. So this is clearly not as good a fit as this is not a statistical uh, determination of this thing, because as you said, these are not uh, we can't actually go should not we should not be going through a statistical fit for the spin at this stage
Yes.
at all. But the comparative ones can be seen that the blue one is 0.99, and while the red one is 0.91. So the actual spin is in between 0.91 and 0.99. And I must tell you that despite all this, remember we are dealing with a turbulent manner which we don't understand at all. There are many systematic theoretical uncertainties which we don't know about. So one should not take this. And precision black hole X-ray binary studies. I don't think is there now or should not be done at this stage.
Okay, so we would rather expect very high frequencies at high spins and a little bit comparatively lower at lower spins. Am I correct?
This is for a single black hole.
Okay, so it's not generalized. We can't, it's too early to say that.
Yes.
Okay, and the last question would be on your penultimate slide. Yes, the previous, yeah, this one. About the uncertainties with the hydrodynamic simulations, I vaguely recall the group in IIT Guwahati, they were emphasizing on the fact that our assumption of the disk itself, the geometry, for example, we are the astronomical community at large is quite obsessed with the Novikov-Thorne thin disk model. So, and it was quite certain to groups that we should be rather using disk geometries which are dynamically evolving with time, taking from sub-Keplerian regimes to Keplerian and so on, where the disk is itself giving rise to a corona instead of having the standard Blamford-Najek mechanism where the corona is always there. So could that also be limiting our analysis? Because in here, I can see the analysis is revolving around Novikov-Thorne.
No, I did not do any nobody has done magnetohydrodynamic simulations for Novikov and Thorne. So
Okay.
that's not we can't do it at all. And of course, I mean, there are specific things that people have been working on, and specific biases in the field. What I've been trying to talk about is consensus. While there's many different opinions about what these things are, none of them have been driven to any consensus in this issue. Okay,
Okay. For instance, many people would like to bank on the TCAF model instead of having Novikov-Thorne.
that,
So do you
that's
have
it.
any comment on that?
No, that's what I'm saying. There's no consensus yet.
Okay.
So we are far from any consensus on what is the right approach for these things.
All right. All right. Thank you, Ranjeev.
Thanks.
Okay, can Ambika, you're already unmuted. Can you go ahead?
Hi
Yes,
Ranjeev,
I,
you hear me?
yes, I can hear
Nice
you.
talk.
Thank you.
Nice talk. A very simple question.
Mm.
When we talk about quasi-periodicity, I would always expect two frequencies incommensurate with each other. So here you talked about some 5 different types of frequencies that can come. Do you think they are all there? They are incommensurate with each other. So do you find any sign of some and different frequencies coming in the power spectrum because of that? Or?
Ambika, I may be the
Yes.
only person now, one of the few people who can answer this question properly. And
Okay.
the answer to the question is nothing to do with physics or astronomy. It's something to do with
Okay.
English.
I see.
The the word quasi-periodic oscillation used by nonlinear dynamics is completely different than the word quasi-periodic oscillation used
Okay.
uh, in the, here. What they mean by quasi-periodic oscillation is just a broad peak in the power spectrum.
Oh, I see. Okay.
So it is just a misfortune that the two scientific words have coincided because maybe they are not heard of each other.
I see.
I mean, of course,
Okay.
the nonlinear dynamic quasi-periodic oscillation is much older, but the astronomers who coined this word had not heard of the nonlinear dynamic quasi-periodic oscillation. So they used this terminology, which is not to be confused with the QPO of the nonlinear
Okay.
dynamics.
Okay then. Good. Thanks.
Thanks.
Okay, KP, can you go ahead and ask your question?
Okay, Ranjeev,
Yes,
two
Kapi.
questions.
Yes.
One is regarding this discontinuity in the fractional RMS versus energy. That, or what you call the pivot point, 1 kV, 100 kV. What is the significance of that?
No, should I go back to the plot just for a second, KP, so that you can missed it. See, if you come here, or let me go.
Yeah.
Let me go to this one better. No, sorry. Okay, let's try this one. This here, the pivot point is here at around 0.2 kV, at around 1 kV.
Yes.
Right now, but the thing is that these pivot points occur only when one of the parameters is varying. If both parameters are varying, like in this plot, there are no pivot points.
Okay.
And
So,
most of the observation we see, at least in the energy range, this is a broad energy range, but if you look at the observations, sorry, I have to go back to the data, sorry, KP. If you look at these observations, you can see that there are no pivot points here between 4 and 80 kV.
right.
But this is may be expected, because if two things are varying, then we don't really expect a pivot point.
Okay, so single parameter, any single parameter?
Yes, like for example, if you have just a cold disk, inner disk temperature varying, then there's a pivot point at some 30-40 kV.
So what is that due to?
Or that is because of the spectrum behaving in mm, this fashion. Ah, like for example, here, if I'm increasing the coldest photon, the spectrum goes up and down like this, and the high energy part is going up down like this. You see, the red one becomes green, and the green one becomes red. So at these energies, there is no motion at all.
Hmm.
There's no movement at all. So that's why the RMS is low here, at around 30 kV.
Okay. Okay. My second question is, you think in your questions that you asked at the end, the jet has anything to do with the truncation of the disk? I mean, and also the role of jet in this whole thing is not there, right? You don't assume any interaction of any of these photons with anything coming from the jets.
Yes, I mean, I'll answer your second question first. Many of the systems, I mean, except for Jazz in 15, we do not see the X-ray spectrum to have I mean, there is a possibility of jet emission above 20-30 kV. So there is a possibility that it could affect it, but we really don't know whether for most like things like Cygnus X1 and all, there's probably no jet emission in the X-rays in the ball. The, but if it is there, it will just complicate matters tremendously. One. The second hope is that if it is there, it is just a 4 to 5% effect, and broad things are still correct in the picture.
Any jets seen, any gamma ray attributed to jets in this case?
No, I mean, so in Cygnus X1 we do see gamma rays. Not Cygnus. We don't see gamma rays in Cygnus X1. GSN 15, of course, has jet, right? But how much does it contribute to X-rays is open question. And your first question about the radius having connection with jet, we don't know whether it's a chicken and egg problem. Whether the truncation of the disk is causing the jet, or the jet is causing the truncation of the disk.
Okay.
I mean, really, I mean, just we can play around with words, but it's just a matter of our ignorance, I think.
Okay. That's all. Thank you.
Thanks.
Okay, Varun, can you unmute yourself and ask your question? Yes, please go ahead.
Hi, Varun. Hello, Varun.
Yes. We can hear you, but not anymore.
I can't hear.
I just heard hello. Hello? We can't hear you, Varun. Hello?
We could go back to chat, perhaps.
Yeah, chat, but nobody is chatting in the chat.
Oh, I see.
What about Paul? Maybe Varun. We can try Paul again. This is Paul Vikas. Can you unmute yourself and try again?
Yes, I have sent.
Right. Now we can hear you better.
There are two questions. One question is there any signature of dimension of the space-time to be understood from the study? Ranjeev? Hello?
I'm afraid because I can't hear you very well.
Yeah, I have sent a chat
Oh, yes.
message.
Okay, then we can read the chat.
But there's no chat, maybe only to Ranjeev. It's not that.
Oh, I see.
Ranjeev, you have to try it.
No, nothing from.
Yeah, there's nothing in the chat window because.
Ah, yeah. I got it. Santosh sir. Is there a signature of I got your question now, because I'll answer. Is there a signature of dimensions of the space-times to be understood? If there, I'm also curious to know if there are any new observations coming out of AstroSat so far. Oh, this is connected to my last point here is a higher order GR, and I guess that's what you are trying to uh, note for. People have been trying that, but not. It is very difficult to disentangle the rest of the things we don't know about turbulence and other aspects of thing with the fact that the GR may still have some modifications. So I think this will require some very fresh sort of data or very innovative ideas to make this happen, right? And for your second question is AstroSat of course AstroSat is observing, and AstroSat has observed so many things, and there's still large amount of data to be analyzed. My personal estimate is that we have taken out, I think, anything between 20 to 30% of the X-ray binary data available with AstroSat till now.
Okay, if there is Desh. Desh, can you unmute yourself? Desh?
Yeah. Okay. Can you hear me?
Yes.
Okay. Yeah. For an outsider trying to understand, when you say about truncated inner disk, talking of the Z thickness being sharply reduced after certain radius, or
I should answer it. No, it is the opposite. The height of the disk actually it goes from a geometrically thin disk to a probably a geometrically thick disk.
I see. So can you just
It is like
briefly
that cartoon which I have here.
right?
You can see that there's a disk and then suddenly it floats up. Sorry, and becomes a
Yeah.
big
So
disk.
that's the inner part, right? Yeah.
Yes, that's right.
Yeah. So is it? So what are the clues of that being very sharp transition?
Oh, we don't know that. We are not sure,
Ah.
except for this. If you associate the quasi-periodic oscillation with those things, with that radius, and then the width of that quasi-periodic oscillation will give you a measure of the sharpness.
I see.
Or, however, we don't have any direct evidence that something like that is sharp.
Okay. Because
In
if it
fact,
were to be changing smoothly, there would be a physical explanation for that, right?
no, I mean, it's a question of how smooth. If it is over the whole scale of disk, then there have been theories like that. Even people have written accretionist theories about what is called a transition regions between the cold disk and the hot disk. And usually what happens is that the transition becomes too big, and then the spectral parameters are not properly matched from that theory. But in general, this is a difficult thing to assess.
Okay. Thanks.
Phil, can you go ahead and ask Ranjeev your question?
Sure. Hi, Ranjeev.
Hi, Phil.
That was a great talk. I loved the fact that you ended your talk by asking all of us questions.
Yes. I should gain something from this talk.
I was just going to comment. You didn't actually, in asking all these questions, there's one other very important parameter that you didn't mention for any of these objects, and that is the orbital period and the nature of the object that's providing the material. And with Cygnus X1, of course, with an extraordinarily bright donor, which is itself Eddington limited at something like over 10 to 38 ergs per second, incredibly bright in the UV. I'd like to think that these are extra parameters which add to the behavior. That it's not just that must influence the structure of the disk. But it's really just a comment. But otherwise, that was a great talk.
I could, yes, Phil, that's of course absolutely true that the orbital parameters and the nature of the system, including one more thing which you have, I'm not sure whether you mentioned or not, is also the abundance of the material which is falling in.
Absolutely.
Which could also affect a lot on how the accretion behavior is going to. But
yeah, I didn't, but I was going to. You're right.
Yeah, but it is the problem is that we have not been able to, I think, put them all in a nice biological categories and species, and so that's these groups of things seems to jump to one another, like mutate to some other things very easily, right? And so that is what. But you're right. That is probably one of the clues which we have to carefully take into account.
Okay, thank you, Phil. Indulekha, can you unmute yourself?
Yeah. My question had to do with this superorbital periods, which Phil Charles was talking about in his earlier talk on ULXs. But since that has been commented on now, I don't have a question.
Okay.
Thanks.
Thank you.
Okay, Arun, can you ask your question? Unmute yourself.
Hi, Ranjeev.
Hi, Arun. Yes.
My question is with respect to KP's question. That pivot point that you showed there, the discontinuity, what would it physically correspond to?
It corresponds to is actually really a pivot point. That means if you take a spectrum which is a power law, and you vary the index,
yes, okay,
then there must be a point where the flux doesn't change.
Okay. It can't be the transition point of that disk, right?
No.
It can't.
This pivot point is a function of energy. It's at a particular photon energy.
Okay. Thanks.
Great. Internet, can you unmute yourself and ask your question? Hello.
Yeah. Hi.
Hi, Niril.
Yeah. So my question is the last one you put. You said that have we verified non-GR gravity? I mean, or non-standard gravity. What do you mean by that? I mean, which
that is my question.
Yes.
But which observation is stoking this question?
Okay, actually, there is now. Okay, just to perspective, people are now looking at a disk spectrum in the soft state, as you may understand,
yes,
in the ultra soft state too, and then they fit it with this Curtis relativistic models of Novikov-Winthrop. You could also put in modified gravity in the Novikov and try to fit that. And what people are doing is, since you cannot put any high dimension modified theories, they're putting parameterize it. Like they have a parameter called M, which moves around from GR to modified gravity. So and they try to see if they can find a constraint on those parameters from those disks, and also from iron line fitting and all. But I am a little skeptical because the other theoretical aspects are not, I don't think, are well. We have good handle on the other theoretical uncertainties to be able to do this.
Okay. All right.
Thank you, Indranil. Can we try Varun once again?
Hello.
Yes, Varun.
Yes, Varun.
Hi, sir. I have a three-part question. Not three-part, three different questions. One is, can you give me a brief sense of the size of the corona and the disk?
Okay, the size of the corona and it is typically considered to be around between 5 to 20 RG gravitational radius.
Okay. And then can you explain, is there any physical explanation of the presence of subharmonic in the power spectrum?
No.
Okay. The third part is...
I love this subject. They're very easy to answer questions.
Third is why is the radius measurement errors are so large? I would imagine the continuum fitting spectra data quality for lag species would be good, right? I mean,
No. In fact, the radius measurement has been possible only through SXT and lag space together, and there are large error bars there. The reason is that you're modeling with an absorption, which is uncertain. You're also modeling the full relativistic disk onto it. On top of it, there is that broad iron line sitting there. So all these things can make the your measurements not that certain. So therefore, the error bars increase.
Okay. Okay. Thank you.
Okay, great. I think, Ranjeev, now we have exhausted all the people's questions.
And time.
So thank you very much to Ranjeev, first of all, for doing this at fairly short notice, and also to everybody for their active participation. Do come back, and we'll have a colloquium next week as well. Thank you, Ranjeev, and thanks everybody.
Thanks.
I don't know how to clap